My name is Juras, and today I'll be presenting Project 1 for our course on Design and Manufacture. Over the next few minutes, I'll be walking you through 5 essential tools and strategies that are widely used in modern engineering, design, and manufacture. These tools help engineers not only create better products, but also reduce errors, save costs, and innovate more effectively. Whether you're developing the next electric vehicle or improving a production line, these strategies form the foundation of engineering excellence. Tools and strategies so important in engineering today. As products become more complex and timelines get shorter, engineers must rely on methods that allow them to quickly design, analyze, and optimize their work. This presentation will focus on 5 key topics: computer-aided design, finite element analysis, design for manufacturability, failure mode and effects analysis, and lean manufacturing. Each of these plays a vital role in the product development cycle, from the first sketch on a screen to the final product rolling off the assembly line. Computer-aided design, or as it's commonly known, CAD. CAD is software that allows engineers to create highly accurate 2D and 3D models. It's used across almost every industry: automotive, aerospace, architecture, electronics, and even fashion. One of the biggest advantages of CAD is precision. Hand drawings can't match the level of detail and accuracy that CAD offers. With features like parametric modeling, engineers can change one dimension and automatically update the rest of the design. CAD also enables collaboration. Multiple engineers can work on the same model, even from different locations, using cloud-based platforms. And of course, it supports rapid prototyping. You can send a CAD file directly to a 3D printer or CNC machine and have a physical prototype in hours. However, CAD does have limitations. The software can be expensive, and it typically requires significant training to use effectively. Shout out 1670. Still, it's hard to imagine modern engineering without it. Element analysis, or as it's colloquially known in the engineering community, FEA. FEA is a powerful simulation tool that models how a design will perform under real-world conditions. For example, it can show how a bridge will bend under load, how heat disperses in an engine, or where cracks might form in a plastic casing. This is especially useful in industries where safety and reliability are critical, like aerospace, automotive, and civil engineering. The beauty of FEA is that it allows engineers to test designs virtually before making a physical prototype. This saves time, money, and materials. For example, imagine you're designing a suspension arm for a car. Before building it, FEA lets you simulate the forces it will experience and identify potential failure points, all without needing a crash test. But there are challenges. The results of FEA are only as good as the mesh quality and assumptions you make. If you oversimplify the model, the simulation might not reflect reality. Also, FEA can be computationally intensive, especially for complex models requiring hours of processing on powerful computers. Despite that, it's become a standard part of the engineering workflow. For manufacturability, or DFM. The idea behind DFM is simple. Design your product in a way that makes it easy and cost-effective to manufacture. This is especially important in mass production. Think of injection molded plastic parts, PCBs, or stamped metal components. A design might look great on screen, but if it's difficult or expensive to manufacture, it might not be practical. DFM encourages engineers to consider manufacturing constraints early in the design process. For example, minimizing the number of parts, standardizing hole sizes, or avoiding complex undercuts that are hard to mold. The benefits are huge: reduced production costs, shorter lead times, and fewer errors during manufacturing. It also minimizes the need for redesigns later on. However, DFM can sometimes limit creativity. To make a product manufacturable, you might have to simplify your design or compromise on aesthetics. But in most cases, the trade-off is worth it, especially when scaling up the product. Is failure mode and effects analysis, or FMEA, as it's spoken shorthandedly often in the engineering world. This is a proactive tool used to identify potential failure points in a product or process and assess how severe the consequences would be. It's widely used in automotive, aerospace, and medical devices, as well as some civil applications, where safety is paramount. The process involves brainstorming all the ways a part or process might fail, assigning a risk priority number, and then taking action to reduce or eliminate the risk. For example, if a battery pack in an electric car could overheat, FMEA would help assess the likelihood, the severity of the outcome, and how easily it could be detected. Based on that, engineers might redesign the cooling system or add sensors. FMEA helps prevent costly recalls, improves reliability, and builds customer trust, which are all impertinent to success in the engineering and business world. That said, it does have limitations. The process can be time-consuming, and the results depend on subjective scoring. It requires input from a cross-functional team to truly be effective. But overall, FMEA is a key part of a good engineering practice. Let's talk about lean manufacturing. Lean is more than just a set of techniques. It's a mindset. The goal is to reduce waste, increase value, and continuously improve. Lean is used in manufacturing, logistics, and even healthcare. It focuses on eliminating non-value added activities like excess inventory, wasting time, waiting time, unnecessary movement. A great example is the Toyota production system, which uses lean principles to produce high-quality cars with minimal waste. Toyota is known for their reliability. Lean encourages team involvement, problem solving, and small ongoing improvements rather than big disruptive changes. The benefits are clear: faster production, better quality, lower costs, and, most importantly from a business perspective, happy customers. But implementing lean isn't easy. It requires a cultural shift. Everyone from managers to line workers needs to be on board, and it takes time. It is not a quick fix. Still, for companies that commit to it, such as Toyota, lean can be transformational. To wrap up, what have we learned? These 5 tools, CAD, FEA, DFM, Design for Manufacturability, FMEA, and Lean Manufacturing, are essential for anyone working in design and manufacturing today. They help engineers create better products, avoid costly mistakes, and improve efficiency across the board. Mastering these tools doesn't just make you a better designer. It makes you a more effective problem solver, communicator, and contributor to any engineering team. Thank you all so much for your attention. I hope this presentation gave you a clearer picture of how these tools work together to drive innovation and success in engineering. I'm happy to take any questions you might have in the comments section below. Please don't forget to subscribe. Are my sources. Thank you.